the beam anywhere within the 2 degrees.
Yeah.
What he's getting at now is is that that's the refractive.
Okay. So let me explain this equation. And in your book has like a kind of a wonky way to make a very, very simple or relatively simple equation exceptionally complicated. Like, I looked at that when I first saw this and going, why? Okay? So, here's the story. And this is all going to fit together with index of refraction eventually. So when you have a double slit experiment, okay, you have two different things. You have the distance between the gaps in the foil, okay? And that's like if you have a light shining behind it like I did with the razor, okay? The other option is that it's what we did with the speakers, and they are 2 point sources of sound or electromagnetic radiation. But no matter what, that value of D, which your book calls little a, why I don't know, but we'll talk about that later. That's the distance between the point sources of either the sound or the electromagnetic radiation. So I'm going to tell you straight up, on Thursday, you're going to have a problem, and this is how they used to do navigation on boats. So they would have, along the coast, they would have radio antennas, and they would broadcast a certain frequency. So imagine what we just did with the speakers. So the speakers would be like the antennas or the radio towers that are broadcasting out this radio signal. You walking along back there would be like the boat, okay? So the little d is going to be the distance either between the radio antennas or the gap in the aluminum foil if you're shining a light behind it, or it's the distance between two speakers if you're talking about sound, okay? Got that?
No.
Tough. Now, L is going to be the distance between the point source and where that signal is detected. Okay? So with you guys, that would be how far you were between the speakers and where you were walking. Okay? That's it. On that screen with the aluminum foil with a laser, that would be the distance between the aluminum foil and the whiteboard. Okay? Got that?
Sure.
Now, this is the wavelength of whatever that is. Okay? Could be, if it's light, that's going to be an extremely small number. If it's a radio, if it's an electromagnetic spectrum like radio waves, that could be a really, really big number. If it's sound, that's going to be whatever that wavelength is. So this value of lambda is going to be determined by whatever that medium is. Now, M is kind of like the harmonics, okay? So unless you're specifically told differently, you just let M equal 1. So M equal 1, 2, 3, 4, basically that tells you how far off of the central maximum you're looking at. So unless you're told differently, you just assume that M equals 1, okay? If it's anything else, you would have to be told, oh, M equals 2, M equals 3, M equals 4. And all that's going to do is spread this delta y out. So the delta y is the distance, so if you can remember that visual. So that delta y is the distance between like the bright spots on the wall, okay? So you've got that central maximum. With you guys, it would be like, hey, I'm in between the middle of the two speakers. This is when I hear the loudest noise. Then how far apart, how far would I have to go before I hear that getting loud again. If it's an electromagnetic spectrum, basically, when am I going to hit constructive interference again? So, here's the beauty of this. When m gets bigger, if you look at this equation, that delta y equals m lambda L over d, first off, look at the units. What units are you going to end up in? You better end up in meters, because if you don't, guess what? The equation fails. So lambda and L are going to be in what? Meters. You're going to divide by meters. So you end up with meters. So here's the story. So typically the D is a fixed value. So if you look at this in terms of your variables, L typically is a fixed value, okay? Because that's the distance from the point source to wherever you're going to have. So basically, usually D and L are fixed values. So if your wavelength gets bigger, what's going to happen to the distance between your central maximums?
It's going to increase.
It's going to increase because you're going to be dividing by a bigger number. Now, here's the reason why. Is that if you look at this in terms of like that double slit experiment, okay? So you have a wave coming through like this. You have a wave coming through like this. And those have to travel a certain wavelength to get to the screen that's behind you, okay? So, to get constructive interference, one of these has to travel a greater distance than the other one does. So if this is your point source here, this one is going to that top blue line is going to travel a shorter distance than the black line is. Okay? Just physically, it doesn't have to travel as far. But if you're going to match up with constructive interference, these have to be off by a whole value of the wavelength. So this might, in a very simplified mathematical model, this would travel L, this would travel 2L. So here's the point on why this works. As that wavelength gets bigger, then that distance between where you're going to get your constructive interference is also going to get bigger, because you physically have a longer wavelength that you have to match up. So if that wavelength is really, really tiny, which is what you saw when I had the light and I had that laser beam on it, and those were very, 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 very close together. And those were very, very close together because light has a really, really, really short wavelength. Radio waves, or sound waves, okay, the sound waves that I tried to model with the speakers, those are much longer wavelengths. So that central maximums in between where it gets reinforced, that distance is much greater because the wavelength is much greater. Now, here's how I hate to say it, I like the College Board and what they do, but I hate what they've done to this equation. So what they've done to this equation, and this is how it's on your sheet. So they have A equals like Y max over L equals M lambda, okay? I have never in my life seen this equation written like this. And if you look at it, it looks completely different than what we just talked about, unless you do some simple algebra. So if you multiply this by L, then you get that M lambda L, and then if you divide by A, then you get basically the change in Y. So this is what's on your equation sheet. Instead of D, which is every other equation in the world for this, which uses D, for whatever reason they decided to put A. Why? I don't know, I just wanted to screen. So this is functionally this equation, okay? And here's what I want you to get out of that, is that this lambda L and D, typically it's your wavelength that gets changed, okay? And then that changes the distance in your relative maximums that you either see or what you hear. Now, index of refraction. So, what's on your equation sheet is N equals C over V. So let me explain how this works. And this is where this will eventually tie back into the equation that we just had, okay? So C is the speed of light, 3.00 times 10 to the 8th meters per second. Technically, that only exists in a vacuum. Thank God our Earth is not a vacuum, or we would not be here having this discussion. But even within the atmosphere of Earth, unless you get real picky, you can just use that 3.00 times 10 to the 8th meters per second as the speed of light. So this is going to be the velocity in a new material, okay? So your index of refraction, the smallest possible index of refraction you could have would be 1. So what's the only way that you can generate an index of refraction of 1?
It's traveling in a vacuum.
Yeah, the two velocities are the same, okay? That's the only way that you can have an index of refraction of 1. Now, this is the velocity in a new material. So let's say the index of refraction is 1.8. So if your N value is 1.8, 3.00 times 10 to the 8th meters per second, how are you going to get the velocity in the new material? Now, just before you do anything, is this velocity in the new material bigger or smaller than 3.00 times 10 to the 8th?
Smaller.
Smaller. So this is why if you ever calculate a velocity using an index of refraction, and you get a number bigger than the speed of light, you have done something horribly wrong, okay? It's like the ultimate speed limit. So how are you going to get this by itself? Charles.
Multiply it to the other side and divide by 1.8.
So somebody take 3.00 times 10 to the 8th meters per second and divide that by 1.8, which has no units because it's just an index.
1.67 times 10 to the 8.
Meters per second. Okay? Cool. Now, this is what we talked about before. My shirt appears blue. If I hold this up and that light travels through that beaker, does my shirt still appear blue?
Yes.
Cool. Now, there's no
There might be.
So the energy of light, and that's what determines your color, is Planck's constant. Don't worry about this, we'll get into Planck's constant later. Is Planck's constant times frequency. Okay, so this is going to turn into a logic situation. So whether that light is just bouncing off my shirt and going out, or if that light is traveling through this beaker, you all see it as blue light. So what that tells me is that when that light travels through that medium, the frequency stays the same. Because if the frequency changed, the energy would change, and it would appear to be a different color. Okay? So if I did that, and it's like, oh, I hold it up, and then it appears blue or red or green, or, you know, like, oh, that got weird real fast. It was like, yeah, it's like this green dot moving across my chest. It doesn't. It stays the same. Now, speed of light equals wavelength times frequency. True? True. Okay? True. 3.00 times 10 to the 8th meters per second. Now, when that light goes through that index of refraction, that speed drops to 1.67 times 10 to the 8th meters per second. Okay? Speed becomes smaller, slows down. Now, I'm going to tell you right now, do not think about this too much. Because you're just going to end up in the corner, sucking your finger, wanting to do drugs.
Uh-oh.
Okay?
Hey,
I'm
we're already
just
halfway there,
no,
Bernie.
no. And here's the reason why, because then you get into what's the mechanism, because light accelerates then, okay?
Wait.
Because it goes, oh, I'm telling you,
Wait a second.
okay?
In order to change colors, it has to accelerate, right?
No, just
No.
stay with me here. So it has to slow down. But guess what? When it goes out of that index of refraction of 1.8, it goes back to normal air. Guess what? It speeds back up.
No.
So it's like, okay, who's controlling the gas pedal on that photon? You know?
Nothing.
How does the energy level just change?
Ooh, magic. Magic. There you go. It's just magic.
I love
Okay.
quantum physics.
Now, we just said that when it goes into that different index of refraction, it has the exact same frequency because my shirt stayed blue. So if the frequency stays the same, but the speed of light becomes smaller, what's the only thing that you can change?
Wavelength.
The wavelength. So what happens to the wavelength of light?
Has to get smaller.
It becomes smaller. So the, what?
Question. What's the acceleration of the speed of light?
Cullen,
Really?
What's that?
How about that?
So.
Here's what I want you to see, is that when that wavelength, the only thing you can change to shrink the speed of light, make it slower, is either you make the wavelength smaller or you make the frequency smaller. Okay? So but here's the catch. If you change the frequency, you change the color. And so, because of the fact that my shirt appears blue, when this goes through, what does that tell you about the frequency? It stays the same. Because the energy stays the same, because color stayed the same. So what happens is that you shrink the wavelength. Okay? Now, let's do a little bit of hocus pocus. Just a little bit. So we just said the index of refraction is C over V, which is the wavelength in a vacuum times the frequency in a vacuum, right? Okay? Well, my new velocity is going to be the wavelength in some new material times the frequency in some new material, right? But what do you know about these two frequencies? They're the same because the color stays the same. So if those stay the same, you can also look at the index of refraction as being the wavelength in a vacuum divided by the wavelength in some new material. Now, your index of refraction has to be bigger than what? 1. So what does that mean about the wavelength of that material? It has to be smaller than the wavelength in the vacuum. Okay? Makes sense. All right, I'm done. Oh, that was an ordeal.
please don't.
So, this is actually out of chapter 17, but Cohen, before you ask, this is all it took me to do. Okay?
Okay.
So, it's pretty short.
You are five. Way too low.
You start with a 5.
Interact with lights.
You're 5'7".
And it's slow down.
This will make your chair.
After like uses that
In the
without
what?
changing the wavelength.
My bad, you're short.
Accelerates your back to your original exact energy.
Did you start with the 5?
Then you won't slow down.
Because I know you're not. No, he's a little
The
L.
black
What's so bad about that?
instantaneously.
What's so bad about the color?
Near.
It's like what? Yes.
If
Light?
it was
Dude, we didn't
instantaneously,
do
what he
that
did,
time. We're
if it
going out to
wasn't
dinner.
instantaneously, there would be a gap when you were walking behind it.
Dude, we started with 5 or 6.
For a high?
Colin, you're overthinking it. It experiences space-time differently.
I'm not gonna have enough time to actually understand.
Number
Think about
12
it in
is the
space. Think of it
easiest
in
problem
time.
on the assignment.
Yes.
Unless you try and make it complicated.
Uh-oh.
Do not make 12 complicated.
I'm really glad that you didn't look at me.
Hey, Bird, I wrote my name on my paper.
Thank you very much.
You're welcome.
Lauren Welsh, on number 7, you're only doing A through C. Note that. Okay? Highlight that. When you get to problem number 7, I only want the angle in degrees.
Boring.
So that problem number 7 is going to deal with an equation that has sine in it, okay? Which is basically, it'll make sense when you get to it. It's a fairly simple calculation. So, anyway, there you go.
Degrees are boring.
Theta is